Okay, so up until now you learned how to provide structure, how to build EPWpy. Now we will perform some calculations and how we do the blocks of EPWpy, we do different blocks of calculation using EPWpy. Now the first step is to perform calculations using EPWpy, and as I showed you in my slides, you need to perform SCF and SCF pH calculation before you can do an EPW calculation. EPWpy basically works on a block-based architecture where each of these block of calculations will be and you can perform using EPWpy. Now, to perform these calculations run inside Quantum Espresso. And to run these calculations inside Quantum Espresso, you actually need a location of Quantum Espresso. You can provide the location of Quantum Espresso by using a keyword called code in the input of the EPWpy class. And here you can provide the location of your Quantum Espresso bin folder where you have installed your executable. In our case, since we have installed EPWpy with Quantum Espresso, we actually do not need this keyword. We can also infer where exactly is my code located. So you can do that by simply performing a print silicon.code. And now if I execute this cell, you can see at the very end that the code is already installed. If you remember, we installed Quantum Espresso EPW 5.9s and the bin location. And this location is already available to EPWpy since you have built Quantum Espresso inside EPWpy. Now we perform some real calculations, and you can perform these calculations using methods which are implemented inside EPWpy. For example, you have a self-consistent field calculation method. And in each of these calculations, for example, you want to perform SCF calculation. As I said, that each calculation requires some kind of preparation, input file, and running. You can do that using simple methods which are implemented inside EPWpy. Every running is a three-step process. So every block can be broken into these three steps, and you need these three steps to execute each block. So for the SCF calculation, you can do silicon.scf. Whatever input you want to provide, which you already did not provide in your material definition. For example, we did not provide the convergence threshold for the electronic ground state SCF calculations. We did not provide the K points. All of those things you can actually provide in these inputs to these methods, and then you can do the preparation and run. Now, in the preparation and run, these first numbers here basically tell you how many cores you are using on your computer. So you can be using an HPC, something like Frontera, where you will have 48 cores, 128 cores, whichever the number of cores that you have requested. And there is a way to request the cores and run Jupyter notebooks with those number of cores that will be discussed in another video. But here you can actually define the number of cores that you want to use, both in the preparation and in the run. And then here basically you define that what type of calculation you want to perform. You want to perform a CF calculation, then the code will launch the pw.x executable. If you want to do a phonon calculation, then EPWpy will actually launch a ph.x calculation. If you want to do an EPW, it will do EPW.x. So this is very important, that what type of calculation you do and what type of preparation you want to do. And based on that, the data will be prepared by EPWpy. And this is the block-based architecture of EPWpy, where each of the blocks have these three definitions, and you need to execute all three of them. Another point is the verbosity. So while you're actually running a calculation, how verbose your output you want to be. Do you want to see the entire output? Do you want to see a portion of the output? Or do you are just worried about how exactly this calculation is progressing? All these three are handled by what we call as the verbosity level in EPWpy. EPWpy currently has 3 verbosity levels. You can control the verbosity by doing silicon.verbosity. equal to 1 or 2 or 3. The default value is 1, which is the lowest level of verbosity, and let us see what it does. So if I do the lowest level of verbosity, I can actually see that the calculation just simply runs. If I do higher level of verbosity, for example 2, then now you can see that it also tells you what exactly is the code that I'm running and what is my parallelization definition, my input file, and the output file that the code is creating, along with the status of the calculation. If you do verbosity level 3, it will actually output the entire file of the scf.out. For in this case, in other cases, it will start outputting all the file. Now, as you can see, this was verbosity. I now know what I'm running, how I'm running. Now here I have something called the parallelization. Parallelization in Quantum Espresso is implemented in various ways, various levels. And you can actually control the type of parallelization you want to do inside EPWpy. So for example, here in the run, you can add a key called the parallelization. And with this, you can actually define what parallelization you want to do. So for example, I want to only perform k-grid parallelization with nk equal to 4. And now if you see, I am actually doing nk equal to 4. I did verbosity equal to 3, and now you can also see that with verbosity 3 it actually prints the entire output. So yes, this is how you run each block. Each block can be controlled completely, and each of these blocks, all the knobs are in your hand. However, all of these can be just simply automated. So this is a simple SCF calculation. And the next point is getting outputs and inferring the output. For example, in a calculation, you also want to have certain things to be outputted. For example, I'm doing a SCF calculation. I want to find the total energy. Those things are also handled by the utilities and the analysis modules of EPWpy. So for example, here I have defined the PW utilities, and with this I can obtain the utilities associated with SCF calculation. For example, I can get the total energy. I can also get the Fermi energy by just simply using another key of eFermi. And as you can see, it outputs the Fermi energy in the electron volts, total energy is in the redbergs. Now, since we have performed EPW SCF calculation, in an EPW calculation we actually have multiple steps, and we will perform now each of them. So the next step is a phonon step that I can perform. Phonon calculations generally take a bit long, but we have used a very simple setting here. We can perform an SCF calculation. Similarly, just like SCF block, you can define your inputs for the phonon blocks. Again, all the keys that are here in this block are the same as the phonon.x input tags. And you can also provide what we call as the Q points. So in certain cases of phonon calculation, you want to restart from the number of Q points, and those can also be provided inside the definition of the phonon method. We can then perform NSCF calculations on the same lines. Again, you can see that in the NSCF calculation, I have defined certain points. For example, I can for NSCF calculation, I can define more number of bands. I need more number of K points. I can perform it on a grid. And all these things are controlled by certain keywords which are provided in the EPWpy. Once you have performed the NSCF calculation, again, if I go back to my slide, You start with an SCF, you have these calculations, and then eventually you perform an EPW calculation, which is of the coarse and fine, and those you can perform using EPW definitions. And the name in the EPW, so if it is EPW1, then it performs the coarse grid unfolding calculation. But if it is EPW greater than 1, so it can be 2, it can be 3, it can be 4, whichever be of your choosing, it will perform interpolation calculation. And the type of calculation, so for example, if you want to perform optical calculation or if you want to perform mobility calculation, those are controlled by the inputs that you provide EPW with. So this is simply the structure of EPWpy, and eventually when you execute these blocks, you will actually perform EPW calculation, and eventually you will get the output.